Thank you, Richard. What we decided to do tonight was, the idea of let's pick a film about robots and then talk about robotics, and that really didn't narrow it down very much. I mean, there's a lot of material out there. So we went through a whole bunch of ideas, but we settled on this one, which we're very excited to screen for you, by Spike Jonze. How many of you have seen it? It's fairly new. It came out last year, and it was shown at Sundance and a couple film festivals. It hasn't really been out in the circuit, and it's because it's 30 minutes long, so it's kind of between a short and a feature. But it's just a marvelous piece of cinema. I'd like to ask everybody in the room to close your eyes for just a second, and I want you to picture a robot. Okay, just hold that thought. You got it in your head? All right. Now open your eyes. All right. Now, how many of you pictured something like this? Okay, how many was like that? Okay, good. How many of you pictured something like this? Any? Okay, good. All right. So we have some industrial robotics people. All right. Those are robots too. How many pictured something like this? Okay, great. So those are all three classes of robots, and the history of robotics goes back quite a long time. This is the idea of automata really go back to the ancients, to the Egyptians, the Greeks. Da Vinci had a robot, Volkanson, and the robot Mechanical Turk that was a chess-playing robot, although it turned out to be a fake. So there's a long history, and what's interesting about these is that they're all mechanical devices. They're beautiful pieces of engineering that involved complex systems of gears and levers and cams, basically very, very complex, like clockwork, to do interesting things. And but then there's this. Okay, so this is the kind of thing that is also kind of thought of as another kind of mechanical being, and this is a whole general class of what we might call Frankenstein, from the Frankenstein myth. It goes back to Faust and Frankenstein and the Golem, and all the way up through the Terminator, and so many of these scary monsters. Now, one of the things the idea is that it plays into this concept of hubris, that in some way to take on a godlike quality of making other beings, that we're going to be punished for that. And so the idea of robots has this really complex dark history, at least in Western culture. And the term itself, the term robot, didn't emerge until 1920. And it came out of Czechoslovakia. A Czech playwright named Karl Čapek used it in a play called Rossum's Universal Robots, RUR. And it was also in the Frankenstein category because the robots revolted and attacked the humans. And but it's interesting that the word itself comes from the Slavic root arbata, which is also German, connects to the German Arbeit, which is the word for work. And it's worker, but not necessarily like having fun, off to work we go. It's kind of like a forced labor. And so, you may recognize that Arbeit macht frei from the Holocaust, from the concentration camp. So it was like, this is not a pleasant kind of association. So it's important to know that history that's connected to this word robot that has this powerful grip on so many of us in culture, and hopefully, had an effect on many of you coming here tonight. Now, there was Asimov, and about 22 years after the word was coined, Asimov comes up with, in a story, he comes up with the 3 laws of robotics. And those, as you can see, are basically about, as he said, it was against the Frankenstein myth that he wanted to categorize the idea that robots didn't necessarily have to be evil or dangerous, that they could actually be protective of people. So the laws were that they would never do harm to humans. And so then that led to a whole host of science fiction and work where robots were well-behaved, essentially like friends of ours. And then we see
How are
things
you
like
doing,
this.
Rosie? Just cleaning the rug, ma'am.
So we all know Rosie the robot, right? She's pretty friendly and helpful. And then this is one of my favorites. Woody Allen from Sleeper. Note this is robotic. Ginsberg and Cohen, they're tailors.
Anybody here? I have a new citizen to be outfitted.
Lotta, you want jackets? We got jackets. You want trousers? We got trousers. This is a good time, believe me. We're having a big sale, tremendous. Positively the lowest prices. Maybe you need a nice double knit.
I love the nose.
I'm stuck with 3 pieces.
The Jewish nose on the
Something
robot.
simple. We got
These are
simple,
Jewish robots.
We got complicated. What are you worried? Move for the waiter.
Okay, and now I want to also come back to, there's official definition of robots, so if you go to certain dictionaries and you look up robots or on the internet, you might see this, which is the definition of the Robot Institute of America. They call it a reprogrammable multifunction manipulator with 3 or more axes. Okay, so because they want to make a distinction between really simple things, that just like a traffic light or a very simple mechanism. They say it's not a robot, it has to have 3 or more axes. But as we've been talking about, there's so much more to the definition than is captured in that. Okay, so there's multiple classes of robots. One thing that in research we talk about the difference between anthropomorphic and non-anthropomorphic robots. And there are many of each type out there. The distinction we like to make is if you think about trying to build an airplane, right? For a long time people wanted airplanes that looked like birds, so they would flap. But it turned out that the actual solution was not to follow birds exactly, right? To have something that was not bird-like, and that was the fixed-wing plane. So something analogous in robotics, that maybe the best robot won't necessarily look like a human. And the thing is that the anthropomorphic type, the humanoid androids, are very commonly thought of for scenarios where they're going to interact with humans. So if they're going to be in your house or things like that, that's what we call unstructured environments, where we don't know what's going to happen. But the other kind is very good for structured environments like factories. And here in the left side, there's an emphasis on flexibility, and on the right side, the emphasis is on efficiency. So I'll just very, very quickly tell you that in the field of robotics, there's lots of work going on. And so I know we have some students here, and if you're interested in this kind of things, we can talk afterward. There's research groups all over the world. I'm very involved with one, with the IEEE Robotics and Automation Society, which has about 6,000 members worldwide and hosts a number of events and conferences, and publishes journals and magazine. And there's all these different areas. So what's also interesting about robotics is it's a highly interdisciplinary field. So we have people from computer science and mechanical engineering and industrial engineering all working together. And some of the topics there's a bunch of math to it, because there's a lot of theory, because you have to really think about, basically robots, I like to think of them as the intersection between the world of computers, which is digital, and the physical world, the natural world, which is analog. And so computers have to bridge that. Robots have to bridge that. So it requires techniques from many, many different areas. There's also a number of different exciting research areas, and this is just one of them, just a few of them. At the last conference, we had over 1,000 papers in about over 100 different sessions. So there's a lot of different areas that are going on. I'll be trying to touch on some of that afterwards. So now I'm going to stop. We're going to switch over and watch the film. Thanks to Spike Jonze and his production company for their permission to show this tonight. And also I want to let you know that if you like the film, there's a book and a copy of the film that you can get from McSweeney's Books. It has a great background on the making of the film and some back material and other things like that. So if you just look for it online, it is available. So with that, I want to move into some of the science part. So first I'm going to show you something that in the course of researching this, one of my students found, and I just love this. This is a project that comes out of the MIT Media Lab. It's called Boxy. So it's a real robot, on the right. But notice it has a very nice resemblance to our hero, Sheldon. I'm going to show you a quick video about what Boxy is all about.
I need help. If you can help me, press the green button on the side of my head.
The project is Boxy. It's an agent that we put out to try to gather stories about a particular environment autonomously. That is, we send it out in the beginning of the day, hope that it will find people, and then ask them questions and find out about the environment.
Hi, my name is Boxy. I'm from the Media Lab and I'm making a movie about MIT. On the side of my head are buttons, so you can give me instructions. If you would like to be part of the movie.
Okay, so actually, what I just want to say really quickly about that is Boxy is a robot, but it's designed to be a robot that's very empathetic, that people will be empathetic to. So they'll talk to it, they'll start to interact with it, and then it's there to collect video, and people pick it up and move it around. And it's a part of his master's thesis. So it's a beautiful piece of actual engineering and science that came out of a very independent source. So I don't think that Alexander Rebin knew about this film, and I don't think Spike Jonze knew about Alexander Rebin. I think they were independent, but they both were thinking along similar lines. If that was a robot that you could empathize with. Okay, so now I want to talk about the scene in the film when the woman yells at her and says, "You can't drive." Remember that? When he's at the bus stop and she says, "You can't drive," that classic woman, "You can't drive." But how many of you know about the Google project, Google car? Okay, so there's actually a very active research project to do exactly this. Actually, it's been going on for 20 years or more. People have been trying to get robots to drive and on highways and streets. And what's particularly interesting about this project, Google's version, which is very successful actually, is that it makes use of the internet. And in the following way, because it makes use of vast amounts of data on roads, a lot of which is available online, and then uses that and integrates that when it makes decisions. So when it's driving around, it's not just looking out cold, it has maps and GPS and vast amounts of information that it's bringing to bear to help it drive accurately. So this is a subset of what I call cloud robotics, and it's a very exciting new sub-area. There's a nice quote I just heard about the car project, this Google car project, and it was Brad Templeton said, "A robot will be truly autonomous when you instruct it to go to work and it decides to go to the beach instead." So I like that. But the bigger picture of the bigger part of this, and I'll talk about for about 10 more minutes now, is called we call cloud robotics. And there's groups at Google and in Europe, a number of researchers are looking into this. And here's the idea: the cloud being the internet. How do we start to think about the cloud as a resource for robots? So as Steve Cousins, who's a CEO of a robot company, said, the way to think about this in a nutshell is no robot is an island. For many years in robotics, we've been building these autonomous creatures that were self-contained. They had processors and everything else, but we just now starting to realize, wait a second, the robot doesn't have to do all the computing on board. It can actually make use of this vast resource that we all use. So let's say we want to do something like this. You know, you've seen the Roomba, the most successful robot ever. 5 million Roombas have been sold. They do something very well, which is sweep the floor. But what if we wanted to go a step further? We want to have Roombas go and actually do more chores around the house, like actually pick things up, like tidy up a room. Well, then it gets more complicated because you really have to do lots more sensing and decision making, so things get tricky. So it turns out that we can start thinking about the cloud as a resource. So the web is very powerful because people are putting up all kinds of information. They're volunteering information. They're helping us with putting up vast amounts of images and databases and tagging images. So, for example, when a robot got stuck, when it's trying to clean around the house and it might see something, it doesn't know what it is, it's not sure if it's let's say a cell phone or a candy bar, what it can do is go up into the cloud and index the cloud and say, you know, here's the shape, here's what I'm seeing, and the cloud, you know, we can use all this indexing that's available to identify, no, that's a Hershey's bar, and it's about 8.5 centimeters long, 4 centimeters wide, etc. So you can get all this information and index it. The other idea is that if your robot really got stuck, it could call a person. So we might have a phone bank of humans standing by, and so a robot's really not sure what to do, and so checks the cloud, can't get an answer, and so it calls the lifeline, right? There's a person, and they upload the information and say, oh, obviously, that's a cell phone, don't throw it out. And then the other thing is the computing power of the cloud. And this is really exciting also, right? There's just zillions of computers out there. And so we can use the computers outside of the robot to do processing. So I want to tell you an example of this that we're doing in our lab at Berkeley. And this is my students and I, a project we're doing where we're essentially trying to figure out how to grasp objects. And what happens is the robot looks down and it sees an object, but it never sees it exactly. So you're always seeing an object imprecisely. And so the idea is that the true object might be any one of these. Right? The robot sensors tell you one thing, but we're not really sure. So now the question is, where do you grasp that? Right? It could be any one of those things. So what we do, the idea is we're going to do that by sampling. We're going to sample different shapes, and for each of those we're going to check different computing strategies, different grasping strategies, and try and find the one that works best. So we call this cloud-based grasping with uncertainty and shape. So without going into all the detail, this is a representation of all the uncertainty in the edges and the vertices of the part, and then these are different approach directions that the gripper can take and their probability of success. So I'm going to give you just a little bit of a description of this. There's a paper that's going to be published in May that we're presenting on this project. And up in the right, how many like science geeks do we have out here? How many people are really into the science part? Okay, came here for the science. Good. All right. So I want to make sure I give you something too. So here's the idea. There are Gaussian distributions around each of the vertices and the center of mass. Okay, so that's a representation of our uncertainty. And then what we want to do is basically compute a grip. And we're going to use a simple grip called the parallel jaw gripper, very common. Two jaws that are going to push the part and then close around it. So in that sequence, as you see there. So we want to compute the optimal pushing direction and closing direction for the grippers. So here's an example of what it looks like in a robot in our lab. So we're pushing and close around this part. Okay. So now, let's see. Yeah. So it turns out that we can characterize the success of a particular grasp direction and approach direction geometrically. So we can look at the properties of its friction and its the torques, and basically what's called the force closure, whether we will successfully grasp the part. We can represent this mechanically as a point in this configuration space. And then what we want to do is check for all kinds of different possible approach directions. We check that against samples of what the part shape might really be. Now, the problem with that is that there's a lot of samples. So that's where the cloud comes in, because we want to do this in parallel. So we basically take one example, we send that out to the cloud where thousands of computers can all process it in parallel. Each one of them sends their report, and then we add those up to come up with an estimated probability, or lower bound on the probability of success for a particular approach direction. So this is the result of it's been computed for a number of shapes. The shapes that you see on the right are brackets. They're kind of weird shapes, and so it's not so obvious where to grasp them, especially with the uncertainty. But what you see in bold on each one of those is the result of what this algorithm computed for the ideal grasp direction. And Q is the lower bound of the probability of success over all of those different perturbations. And and so for example, this is an example where these three grasps on the bottom all look pretty reasonable to me. I mean, I think to most of us that they all seem like they would be good. But it turns out that when we did the analysis, the first one, the second one are actually fairly good, but the last one is actually very bad. It has a very low probability of success. Because again, how it will respond to the center of mass as it gets pushed. And so we did an experiment with that last one, and exactly as predicted, it doesn't succeed. So it's interesting that we can come up with counterintuitive results, that the computer actually does things that basically logically analyzes this and finds something that we wouldn't have intuitively figured out. Okay, so Good, and so then, as I say, the idea is that we can do this computation in the cloud, so we can do it in parallel, and then we can do vast amounts of these very quickly. Here's a scene from what it might.
Fly that thing?
Here's the cloud.
Not yet.
From the Matrix.
Jack, I need a pilot program for a B-212 helicopter. Hurry.
So she's going to the cloud.
Let's go.
All right. So the idea is like, let's use the cloud as a great resource for computing. Okay, so now let's go back to another scene from the movie, which is near the end, which is the surgery. And I want to talk next about robot-assisted surgery. And this is a very big area right now. It's enormously important. And one of the projects I'm working on is with University UC San Francisco, where they're doing radiation oncology. And here's a sort of illustration of the technique. When you have a cancerous tumor, there's a technique called brachytherapy. And the idea is that they put in these needles in parallel into the body, and then they insert radioactive seeds through the needles into the tumor, and the idea is that the radioactive seeds will stay there and decay and kill the tumor and hopefully spare the healthy tissue. But one of the big problems is the way, as you can see there, that the arrangement, the template that they've been using for the last 20 years, forces all the needles to be parallel. So what happens is that there may be an organ in the way, and you have to sort of jam right through it. And it turns out, and I won't go into the gory details, but it turns out that for prostate, which is what this is commonly used for, there's some organs that you don't really want to have needles going through. Okay, so that causes all kinds of side effects. And so it turns out that we started talking, the surgeons there, the doctors started saying, well, what we really want to do is have needles coming in from different angles so we can avoid the sensitive organs. So here's what that might look like. So notice that the needles are not parallel anymore. They're called skew arrangements, skew lines, non-parallel linear segments. And what we want to do then is, but now it's tricky because how is the surgeon going to get those in at the precise positions and orientations? But this is where a robot comes in, right? Because we can have a robot help guide the needles and avoid the delicate organs but still reach the target to kill the tumor. So it turns out there's a lot of related work. Other people have been looking into this from different perspectives. But we have a new algorithm that just got published. Actually, I should say it's under review by Medical Physics, and it's an algorithm for computing the optimal arrangement of needles. And then it turns out that's actually a hard problem, computationally hard problem to solve, to figure it out. But one of my students had figured out a very nice approach to it that is showing a lot of promise in being able to compute these very, very quickly. And so you can see here that we use these conical arrangements. So instead of only parallel, he also introduces conical, and these can avoid the delicate organs that are at the base. And what he's been able to show is that this allows us to not only avoid the delicate organs, but also reduce the number of needles that you need. So typically before you use about 16 needles, but we've been able to show that you can actually reduce the number of needles lower. Now you sacrifice something in what has to do with the robustness. So this is something we're investigating, but basically it's a very positive idea that we can compute things that are better than the treatment that's better than what's being done now, and avoid the sensitive tissues. So, and then we did an experiment. These are some of the experiments that show that with the skew arrangement, here's with 16 needles, but we can completely avoid intersecting with the delicate tissues. And then this is a flow of how the process works, how we take the data, we build a CAD model, a CT model of the organs, then we compute the optimal arrangement, and then we have to execute that arrangement. We have to do the delivery, and that's what the robot part is. And this is a new robot that was developed by a colleague of ours at Johns Hopkins, so we're collaborating. He sent the robot, it's called AccuBot, to us last fall, and then we did these experiments on what's called a phantom. So it's just gelatinous material, but it's anatomically accurate. And so you see that the robot is guiding these needles in at very precise angles to avoid, this is a model of the sensitive tissue, and wants to reach the target. Good. All right. So that's one project. The other one has to do with the Da Vinci. And how many of you know about the Da Vinci surgical robots? Seen those around? Yeah. So these are incredibly successful. They're in use now in over 2,000 hospitals around the world, and they are used for many different procedures. Gallbladder, prostate. My daughter here had her appendix taken out with one of these systems. So the Da Vinci is a very powerful system, and the idea of it, though, is that it is set up to precisely allow the surgeon to work comfortably over here, and then the robot repeats the motions inside the body. But the limitation is that right now it's just in a pure master-slave mode. So the human is doing the controlling, and the robot is following. But the robot isn't doing anything on its own. So we started wondering if it would be interesting that some of these tasks, what if we could let the robot do those on its own? So not the whole surgery, because it's very complex, and I don't think we're going to replace the human surgeon completely. But there's some subtasks that are very tedious and like suturing that we could imagine the robot could do on its own. So in order to do that, what we want to do is have something like this. We want to program the robot to do what you see on the top. Well, it turns out it's really hard. So because you're dealing with tissue and complex motions, and it's very difficult. So it turns out that there was a colleague who had been working on robot learning. That is where you have a human train the robot to do a complex task like this. So here's the idea. Imagine we want the robot to perform a figure eight, just as an illustration. Okay. What we do is we ask the human to control the robot to perform a figure eight. Right. So this is exactly what you see on the bottom. This is the human is controlling the robot. Right. So the result is kind of, it's much better than actually what an amateur like me could do, because they're experts. But still, it's kind of imprecise and jerky. So what we do is we now take those examples, the demonstrations that we recorded, and we process those. First of all, we time align them, because each one is some are slightly longer or shorter than others. So we use a technique from speech recognition called dynamic time warping. And what that does is allows you to line up all the examples together. And then we apply a technique called Kalman smoothing that allows us to take all the examples and infer an optimal underlying trajectory that's underneath them, where basically it treats all of the examples as noisy observations of an underlying control trajectory. So we then we can take those noisy observations, and this is what we compute. This is what the software has analyzed from that to compute. This is what was underlying the controls to generate the robot to do this. So then what we do is, let me back up. So what we now do is we have this trajectory we've inferred, so we've computed that, and we execute that on the robot, and we see what happens. And then we have to fine-tune it a little bit. So we have to adjust the controls, the parameters, just a little bit to get it back on track. And then we speed it up, we increase the velocity. So then we run it again, and again we fine-tune it. This is a process called iterative learning. And we keep doing that, keep speeding it up faster and faster, because what we'd like to do is have something that can not only suture like a doctor, but can do it faster than a doctor. So here's the result of that being executed at the speed of the surgeons. Here's at 4 times. Here's the result at 7 times. And here's the result at 10 times. So notice that as we've gotten faster, actually the trajectory gets smoother and actually gets very close approximation to what we wanted with the ideal figure 8 trajectory. There's very exciting possibilities of what we can do with this. And I'll show you what it looks like in this is a system that we are now working with. We just got a piece of hardware system called the Raven, which is like the Da Vinci, but is completely open source. So we have complete access to all aspects of the system. And we just got this from a National Science Foundation grant from the University of Washington. And here's some initial experiments of this is the surgeon operating it. So just the idea is to touch 4 corners of the box. Okay, but now we've learned it. Now we're going to re-execute this at 4 times speed of the surgeon. Here's 8 times the speed. And then here's 10 times the speed. Now, I can't show you 12 times because the cables broke at that point. But it's a really exciting thing for us right now. So now we're applying this to suturing and other scenarios. So these are examples of medical robotics, and it's a huge and growing field. It's a very exciting because it's really, there's been a paradigm shift where doctors have really embraced robotics technology, and it's being used in many, many different aspects of medical treatment. Right, now I'm going to switch gears a little bit. Let's look at the faces, beautiful faces that Spike Jonze and his art directors made for the robots. This is a robot that I really love, and it's called Kiva Systems. So Kiva Systems was designed by Raf D'Andrea, a brilliant robotics designer, and these are the little orange things are the robots. If you look closely, they actually look a lot like Sheldon. And what they are is it's just a little platform. But the beauty of it is that they move these racks around in a warehouse. So they do logistics. So the human just stands there, and basically humans are very good at loading and unloading, recognizing things. So imagine it like Amazon. They have these vast warehouses, and when they get an order, they have to figure out, well, I need this, 2 of these, 3 of these, etc. So the robots help basically move the books to them. They can assemble them and put them into the boxes. So it's a hybrid system because you have humans and robots working together. And it's very successful. They're using this in a lot of different major warehouse and logistics centers. Now the other thing is, let's look at now I want to look at the issue of walking, because these robots in the film, right, were able to walk, at least when they had 2 feet. So here's an example of a very new system that's been under development at Boston Dynamics. A researcher named Mark Raybert has developed a walking machine. And look at it in action. It's got a beautiful gait, doesn't it? A general example of something called service or home robotics, and we're working on it. Okay, so we got a long way to go. What's actually important about this result is that, and it's been published in a number of journals, is that actually because it folded 50 towels in a row without a failure. That's pretty amazing because the towels are all crumpled up, so it has to figure out how to grab the corners of the towel and rearrange it. But 50 in a row took a long